Number 39. A sample of rock was found to contain 8.23 milligrams of rubidium-87 and 0.47 milligrams of strontium-87. Letter A. Calculate the age of the rock if the half-life of the decay of rubidium by beta emission is 4.7 times 10 to the 10th years. That's crazy. So this rubidium, right, it takes 4.7 times 10 to the 10th years to decompose to half of its original value. That's a long time. But either way, with that half-life and what they told me, we have to basically find out that total age of the rock. How old is this rock? Okay, so the first thing is that, I got two different metals here, right? I got rubidium-87 and then strontium-87. Now, they did say that rubidium is going to undergo beta emission. So maybe the first thing is to just kind of draw out a nuclear reaction, right? A balanced equation using those nuclide notations. Now, whenever we're doing nuclide notation, remember it's those three boxes, right? These right here. Now, they did say that it was rubidium that is decaying. So I'm going to take this guy, the rubidium-87, and I'm going to undergo beta emission. So rubidium, I believe, is Rb. So Rb, always the values that they tell you, 87, that's always going to be the atomic mass or the mass number. Doesn't really matter, for this case, it doesn't really matter what word you use, but just know that the mass numbers, they can change for your element. So they have to specify which one we're using. So the mass number always goes on top, 87 goes on top, and the bottom number, right, if this is the mass number, and maybe I'll pull this a little bit out, mass number, okay. The bottom number is the atomic number. That's the number that doesn't change for any element. And we're getting a little close here. So let's see, maybe I could push this. Good. Okay, let me just actually push this over here on my end. Okay, cool. So I'm going to go on the periodic table, and I'm going to find out what that atomic number is for rubidium. So I see big old whole number 37. Okay, so we're good here. Now it's undergoing to go beta emission, right? And if you're emitting anything, it doesn't matter whether it's alpha emission, beta emission, positron emission. Emission means that you're emitting whatever they're talking about into the atmosphere. So it's kind of like a release idea. It's releasing a beta particle. So I know that this guy, when it breaks down, it's going to release that beta particle, and the beta particle is the same thing as saying an electron. So let's do our nuclide notation. We have a beta. Now it doesn't matter whether you put the B or the E because they're identical, but we'll say beta particle. I like to use the B, so let's do that. And just know that a beta particle and electron is not in the nucleus, so it doesn't have a mass number. And the charge of an electron is a -1. Now we're going to make the other nuclide, right? What does that rubidium actually turn into when it loses an electron? Well, the top numbers, remember, got to equal across the yield sign, and the bottom numbers have to equal across that yield sign. So 87, you could think about this as equals. 87 equals 0 plus 87, and 37 equals -1 plus what? Well, it would have to be one number higher, 38. 38 minus 1 equals 37. And now, we always go on the periodic table and look for the atomic number, because remember, the atomic number is never going to change. So, numero 38 is the strontium, so Sr. And that's what they said here. All right, so the puzzle is slowly unraveling, right? They did say that I had 8.23 milligrams of this, but then they said that I had maybe I can just erase this. They did say that I had 0.47 milligrams of the strontium. Now look at these mass differences, right? This is much greater than this. It does seem that this was only produced because the rubidium started breaking down, right? If you had a sample that was predominantly or all rubidium, and you start breaking down by your, nuclide equation, of course you're going to make a little bit of your more stable particle. So by this being really, really small, we can assume that this actually came from the RB. And this was only produced because that the RB broke down. That's going to play an important factor here. So let's just think about that. Now, let's see. We want to still calculate that age, right? And if it's 10 years old, right? For things that have shorter half-lives, maybe it's, only, 20 days old, right? Could be days, could be years, right? That's still a length of time, right? It's just a length of time that basically has just passed by, right? If you're 21 years old, 21 years has passed. So whenever they're asking for calculate the age, all they're looking for is a secret time. Okay, now, big thing here is that because we're in the nuclear chapter, right? Or if you're doing this problem, you should be in nuclear chemistry, the chapter nuclear chemistry, and they love to give you new formulas. However, chances are, if you're in your nuclear chemistry chapter, you've probably already done kinetics. Generally, nuclear chem is like the last thing that, teachers or professors teach. And just know that all of your radioactive activity, so anytime that you're emitting particles, or basically this whole chapter, any type of radioactive decay, is always going to go under, we'll say, what's that called? First order. It's always first order kinetics. So, literally, the equations that you learned from your kinetics chapter for first order is always going to be these formulas. So, radioactive decay is always first order kinetics. So why learn a different formula just because it's a different chapter when you already have your first order kinetic equations, which I wrote down here, right? You got a half-life equation, T half equals 0.693 over K. And then you got your integrated rate law, the ln of an amount, a concentration, equals negative KT plus the ln of your initial amount. So those are the ones that I'm going to use. Now, if we're trying to find out the half, or not even here, we're trying to find just a regular time, right? Not the half-life, because they already told us that the half-life was 4.7 times 10 to the 10th years. So we're looking for a general T value. And I have two equations for first order. This is the only one that has that T. So it seems to me like we're definitely going to have to use this formula. Now, let's see how far we can get. Now, the T is what we're searching for, so that's definitely going to be X, or you can leave it as, lowercase t. This is the time, the general time that they're talking about. But now, if I'm using this formula, I have to know a K value. And the K value is always the rate constant. But if I read this question again, they didn't tell me anything about having a rate constant. So I can't really use this formula yet because I don't have that K value. Generally, if you're using, formulas, you should only have one variable. So if I'm solving for T, I have to know these three things. But now what's the other formula for first order? Oh, half-life equals 0.693 divided by K. Did they give us the half-life? They sure did. So what I'm going to do is I'm just going to put this on the back burner over here. And let's now work over here just to get that K value. Now, they did say that my half-life was 4.7 times 10 to the 10th years. And we're just going to solve for K. So let's go for it, right? So 4.7 times 10 to the 10th equals some 0.693 divided by Decay. We can cross multiply and then do our little division, right? Just drawing it out, just for you guys. 4.7, let me just push this up. Boop, okay. 4.7 times 10 to the 10th times K equals 0.693. Gotta solve for K, divide by that value, and we're gonna get a really, really, really small number. But that is totally okay. 4K. So 0.693 divided by 4.7 times 10 to the 10th. Just making sure that everything looks good on my end. 0.693 divided by that. That looks good to me. Okay, we have a very, very small K value. So my rate constant is 1.47 times 10 to the negative 11th. And since we use years as our half-life value, technically the rate constant should be in years to the minus 1. So it's just whatever your time value is, just with the minus 1 per year. So now we have this K value. Okay, cool. So 1.47 times 10 to the negative 11th years. Okay, so pause the video because we don't need this formula anymore, and there's obviously some more math that we're going to do. So we're just going to clean this up a little bit. If you do need to write it down, here you go, but it's going to go in 3, 2, 1. Okay. Now, let's bring this over. We found out the K value, bada bing, bada boom. This was negative 11. And now the only thing I need is these two values. Now let's see. These stand for the amount of your material that is decomposing. So these brackets stand for molarities, but you don't have to use molarity. You could use grams, you could use milligrams. It doesn't matter. You could use moles, right? They just have to be the same unit. That's the beauty of this formula. Now, in this case, we're talking about the rubidium because the rubidium is the one that is decomposing or changing. Keep in mind that this value is always going to be your initial amount, and this one is going to be the final. And just make sure that when you're using this formula, this is always the final amount that's remaining. It is not how much is gone. So sometimes questions will try to trick you because they'll actually tell you how much is gone, but you would need to do subtraction to find out how much is remaining, or do something, right? Now let's go back to these milligrams. Now they did tell me that I had 8.23 milligrams, right? They found a random sample of this rock, and at that point in time, it had 8.23 milligrams of the rubidium. Now we have to find out, is that 8.23 going in the final amount, or was that the initial amount? Did you say final? If you did, you're absolutely correct. This is literally how much is in the rock at this present moment. This was not the starting amount. Keep in mind that it broke down into strontium, right? This 0.47 milligrams actually came from the rubidium in the beginning. In the beginning, that's initial. So we know that at this stage of the game, we have 8.23 milligrams of the rubidium remaining. But now, do we know how much there was initially? They didn't say. We definitely have to find it because I need to plug it into there, but we have to find it out somehow, right? Well, let's see. Now this equation is going on the back burner again. And we have to find out how to find this initial amount out. Well, the only thing that they told me was that the 0.47 milligrams of strontium was made. And I got a balance equation here. So we could do a little stoichiometry to go from the strontium-87, right? the milligrams, so that 0.47 milligrams, to go to how much rubidium was that? Okay, coming back to stoich. Now remember, when you're converting from one substance to another, it's always through the unit of moles, which comes from grams. So just make sure that you have this value in grams. Milligrams to grams is always dividing by 1,000. So we do have to take that 0.47. I'm just going to divide it by 1,000 here just so I have that number ready to go. But this is going to be 4.7 times 10 to the fourth, negative fourth, grams of the SR. Now, let's go for it, right? 4.7 times 10 to the negative fourth grams of the strontium. We don't want the strontium anymore, so that's got to go in the bottom. We're converting here. We're using stoichiometry. So grams of SR go on the bottom. We got to go to moles of SR. 1 mole of strontium equals the mass that the strontium had, right? And in this case, they did tell us that the strontium was 87. So we're going to put that 87 down at the bottom here. Okay, so grams of strontium will cancel out. Now we have moles of strontium. We don't want that. We want to go back to rubidium. So we make a little fraction again. Mole of strontium on the bottom. We want to go to moles of rubidium, so that goes on the top. This is now your balanced equation. But for any nuclear reaction, right, if you don't see any big numbers in the front, it's always 1. So in this case, it's 1 to 1. Now, we just have to go back to the milligrams, right? So let's just convert over. Moles of rubidium on the bottom, grams of rubidium up on the top. They did tell us that the rubidium was 87 grams for every 1 mole, right? This is using the mass number. Moles of rubidium will cancel out, and you have grams. But now here's an interesting thing, though, right? Because I have 87 on the bottom and 87 on the top. What's going to happen to these values? Yeah, they're going to cancel, and everything else is 1. So it's going to be the same amount of grams. But just make sure that if they don't give you the same amount, let's just say that this was 87 and this was, 89 because it was some type of other emission, the numbers will change. So just make sure of that, okay? So if this is 4.7 times 10 to the negative fourth grams of rubidium, this is the same thing as saying 0.47 milligrams of rubidium. That's how much got converted. So let's pause the video. All we just need to understand now is that all of this value, the 0.47 milligrams, turned into 0.47 milligrams of the rubidium. So pause the video if you do need this. Just make sure that, the masses didn't change. So I'm going to get rid of this. Goodbye. And now, this is how much has decayed. Well, we know that we have 8.23 milligrams remaining. And if 0.47 milligrams decayed, we're just going to add the two together, because that's going to be now the total amount that was initially in the beginning. So 8.23 plus 0.47, you get 8.7. And now we finally have that initial amount. The initial amount is 8.7 milligrams. So we now have everything. Finally, we're going back to this equation. We're going to solve for that time. So let's just plug it in. So let's see. We might have enough room here. ln of equals negative. I'm just kind of putting the brackets together. Plus ln of, we'll pull this down a little bit. Okay, So we got ln of 8.23 equals negative the K value 1.47 times 10 to the negative 11th times the X value plus ln of 8.7. So now we can just simplify this by getting the two ln values and then use our PEMDAS, right? So let's see, ln of 8.23. I'm going to round on the screen, but when I do my calculations, I won't round. So 2.178 equals negative 1.47 times 10 to the negative 11 times x. And then we do ln of 8.7 plus 2.1633. Okay, you want to get x by itself, so let's subtract that 2.1633 on both sides. Okay, that goes bye-bye. And now I'm just going to take the full numbers. So we're going to take this value minus this value. Negative 0.0555 equals negative 1.47 times 10 to the negative 11th times x. We still want to solve for x, so we're going to divide on both sides by that negative k value, negative 1.47. And I might have the actual full number that I can take. Let's see, if I go all the way up, so it's going to be this value divided by, I love my TI-84. Where was the 1? Here we go. And maybe I'll just make that value a negative. Let's see if that worked. Whoop. I'm going to put in a negative value in there. So we're going to insert a negative. There we go. And I think we're good. Let's press enter. The numbers look good. That's a really old rock. T equals, I guess we'll do 2 sig figs. So I guess we'll do 3.8. Does anybody care about sig figs here? No. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're in the units of years. So this rock has been through a lot of stuff. It might need therapy. It's seen a lot of stuff. So it's 3.8 times 10 to the 9th years old. And that is only letter A. So calculate the age of the rock. It's 3.8 times 10 to the 9th years old. Because 3.8 times 10 to the 9th years has passed by. Okay, so now we have to just do B. So what we're going to do is just pause the video. We just need a little bit of more room. So we don't really need this anymore. So that's going to go. This is the answer for part A. So I'm just going to put an A value here. And I think I have enough space for a B. Because this one is kind of like a concept question. What kind of box was that, Christina? Come on. That's killing me. That is really killing me, that one line. Does anybody know who I am on this channel? With my, everything's always got to be centered. Okay. So here we go. So it says B. If some of that strontium, right? If some of that strontium, this guy right here, was initially present in the rock, would the rock be younger, older, or the same age as the age that we calculated in A? Okay, so let's reason this out. So if the SR-87 was initially always present, or some of it at least, right? That means that you would basically have a less amount that came from rubidium, right? Because let's just pretend that if if out of this amount, some was initially present, maybe we'll say that 0.30 was initially present, that means that 0.17, because we add the two together to get 0.47, that means that only this amount was coming from the rubidium. So because of that, that means that this added number is going to be lower, right? And if we have a lower added amount, that means that this value would be lower. So instead of dealing with 8.7 milligrams, we would be dealing with something that is less. So in part A, we went from 8.7 milligrams down to 8.23. Now, we know that we have to just go somehow less. I don't know, pick any number. It just has to be, greater than 8.23 because you can't start off with less than what you decayed to. So maybe now it's like 8.4 milligrams. And you went down to 8.23. Would this have a longer amount of time? Would it have a shorter amount of time? Or would it be the same exact age? Well, in order to really check this out, what I would do is I would just plug this value in. Instead of 8.7, try 8.4 and see if that time is a higher value or a lower value. Now, we can make an estimated guess, right? What would you think? Do you think that the rock would be younger? If you did, you're absolutely correct. The less amount that it decays, that means the less time went on, right? The more amount that it decayed, that means more time went on. So as more decays, more time has totally went on. So if you're starting out at 8.4 and you're only, decaying to the same amount, then it definitely has to be younger. But just to kind of go through, your conceptual thinking versus finding it out algebraically, we did make an estimated guess. You could always plug in just a lower value, in our case, 8.4, and just see if that time is lower. And I will assure you that it will be. So in this case, that rock would be younger. And that's it. What'd you think? This one was a crazy one, but I hope it helped. Thank you so much for being here with me and watching the video as we do chemistry together. Thank you so much for all your support thus far in this journey. I really love helping you guys out. My brother and I, we really do appreciate each and every one of you. Thank you so much. For all of you who want to help out the channel a little more, there's always memberships, which we just opened for this new school year. So if you want to check it out, you totally can, but obviously it's not obligated, not mandatory. You guys are awesome anyway. You help us out by watching the video. So thank you so much. I hope you're having an amazing day. Keep studying hard, and I'll talk to you soon, okay? All right, bye-bye.